Okay. Not sure which screen did I share here. Two. Okay. All right. So this is part 2 of the linear programming that we have. This is another example. We had other examples last week. So here we are going to also see an example that we can use, or case that we can use sensitivity analysis and the shadow cards, reduced cost concept that we had example before. Help you to enforce and learn it better. So let's see what the example is. The General Flakes Corporation sells a low-fat breakfast cereal that appeals to men and women of all ages. GFC advertises this cereal with 30-second TV slot on various TV shows, for example, The Revenge, the Sunday Night Football, The Simpsons, etc., etc. Ads differ by the cost and the number of viewers that they can get based on some, I think, Nielsen data that they have to reach in each of the 6 demographic groups. So we have men and women, different range group or age groups. We have men 18 to 35 years old, men 36 to 55, men 56 and older. Then we have the same brackets for women age 18 to 35, 36 to 55, and 56 and older. So each ad viewer is called an exposure graph. So we have got this table that shows all the information that we needed. So this is the ad exposure, the values are in million viewers. And you can see the demographic groups, the 6 groups that we have on each row. And on the column, you can see the TV shows, The Revenge, the Sunday Night Football, Simpsons, the Sports Center, Homeland, Rachel Ray, CNN, The Good Life. For example, for Revenge, the exposure for the demographic group, men 18 to 35, is 5 million. Okay? These are estimated value they have. The other values you can see here. And on the last row here, you see the cost per ad in $1,000 for each show. For example, for Revenge is 140,000. For SNF is 100, and you can see for CNN is less than all of them. It's 8,000. It's cheaper than most of them. And if you look at the views that they can reach, is the smallest of them all. Looks like people don't get the news from the news. All right. Okay, so here's what they want to do. They want to see who should actually sell their cereal. They know who they want to sell their cereals to, so they have like a minimum demographic reach for the 6 demographic groups. For example, here, this is the minimum required exposure that they expect to get from the first demographic, 18 men 18 to 35. They want to reach at least 60 million. From men 36 to 55, 60 million. 56 to older, not much, 28 million. For the woman, it's the same, 60 million, 28 for 28 million for women older than 56. Okay, so ad agencies usually can supply these exposure data based on the Nielsen ratings. What is the goal here? They want to find a plan for running ad on these TV shows so that they can actually reach the minimum exposure that they have for each demographic groups that I showed you here, 60 million, 60 million. But at the least cost possible, because as you can see, each show has various or different actually costs per ad. So that's the goal. So what's the first step? As we talked about it, we're going to go to influence charts. Honestly, this is like a pre-step of solving the problem. I would say for some problem, this could be harder than like writing the model. I think for this specific problem could be. For me personally, I actually, it's easier for me to just go right ahead and formulate the problem as linear programming than try to find this influence chart. But for some other problems, I think this would help more. But just remember that this is not the goal. Developing an influence chart is not a goal. It's just to have a tool to help you understand the problem better and then develop the model. Okay. So again, you start from just explaining how it goes. You start from the output. So the output is to minimize the total cost of the ad plans. And what goes into this, or what influences the cost, is going to be our own decision of the ad plan. How many ads should we run on different shows? So that's going to be also our decision too. So that's why you see actually go back and forth here. And the other one is the cost per ad for each different show. Our decision itself is going to actually also dictate the total exposure per demographic group, which has to be greater than or equal to the requirement for the company. And this total exposure also influenced by the exposure per ad for demographic group. So again, this is not, this is a step to write the model. If you feel you're more comfortable or easier for you to go a step on into formulating the model right away, sometimes it's actually better to do it back and forth, to go to model, to try to see if you can model it. If you see some problem, then go back to the influencer and try to develop that one a little bit better, and then go back to the model. All right, so as we did for every problem that we solve in Excel, we try to write out the components, the inputs, decision variables, output, etc., etc. So here the inputs for Excel is going to be the exposure per ad for each demographic group. These are the data that we have. We also have the required exposure for each demographic group, and we have also the cost per ad for each shows. And our decision variables is for 8 different TV shows that we have, how many TV ads should be run. So that's actually going to be our advertising plan, I'm going to call it. And then we're going to have 6 constraints for each demographic groups. And the goal is to meet or exceed the minimum requirement for each age group. For example, men 18 to 35, at least 60 million. And the objective is to minimize the total cost of these ad plans that meet our required views. We're going to use the range names to make the model easier to understand, and also for future references when you want to come back to the model or share it with somebody, it actually make it much easier, as you have seen with the models that we have done. And also remember that we have left-hand side, right-hand side, the objective function. So we're going to see all these components of the model there, and then we're going to go to this solver dialog. Okay. All right, so let's go to the Excel file. So I have uploaded the Excel data file that you need, and also the done version of this model that I'm going to run here. Let me open it. Advertising data. All right, so this is the Excel that shows the data that we need. So the sheet just says the sheet name is data, and the advertising model as we used to do it here. Then we have listed all the inputs here. We have followed all the format that we have. The blue, as you can remember, we had white, blank, the red for decision variable, inputs, outputs, etc. So all of these are inputs because these are our data. And you can see our 6 range group and also the 8 TV shows. So these are the data that I showed you in the Excel, in the PowerPoint. And these are the costs per ad for each TV shows. Okay. All right, so let's get started with our model. So what we need our decision variables. So let's go ahead and do that. I'm gonna call that our advertising plan. I'm gonna format it the way we did it before. So we're gonna have 8 advertising plans for each TV shows. I'm gonna use the decision variable theme here, and this is going to be for some, to make it easier for you to see these. I'm gonna copy these, the name of these TV shows here, so you know that this is for revenge, this is for something, night football, etc., etc. And let's actually use the range name to for simplicity, and also when we want to model it in Solver, it will be easy to see it rather than seeing, for example, B15, C13, etc., etc. So I'm gonna use the range names here by going to the formula, then create from selection, and left column, okay. All right, so that's done. And now we're gonna go to the objective function. So I'm gonna name this the total cost. So the total cost is just multiplication of the cost for each TV shows and the amount of app that we have run for that show. So I'm gonna use some product here instead of multiplying each show by its decision variable. I'm gonna use the sum product. So I'm gonna select all these ranges for the total cost multiplied by decision. It is right now 0 because these are empty. So I'm gonna just give them some random values here. Let's align this into center align. Okay, and also use the theme for this, the output format. Okay. But you see, as I said, my preference is to use the yellow color, but the text we use is the gray color. All right, so this is done. What else? We had also the minimum ad exposure requirement for each group actually here in the data. So I'm gonna put that as an input here for each age group and also demographic group here. Okay, so I'm gonna put it here and I'm gonna call it required exposure. Right, required exposure, I'm gonna write the numbers here. So we have 60, 28 million, 60 million, 60 million. By the way, again, these values are in million, and also the costs are in $1,000, okay, as we say here. So also these values are in million, and 28 million for the woman 56 and older. So I'm gonna use my input here. So this is our requirement. We want to, whatever decision we make here, for this demographic group, we want to reach at least, or the exposure requirement is this. So that means that we need actually one more computation calculation part here is this, based on this decision variable, how much we can get exposure for each demographic group. For example, right now, we run one advertise for the revenge show, and the revenge show gets 5 million views for the men 18 to 35. Okay? So I'm gonna create another column here. I'm gonna call it the actual exposure. Actual exposure. And that's going to be this. Okay, I'm gonna use some product. So it should be for men 18 to 35, whatever show we run here, depending on our decision variable here. What's going to happen is we want to multiply our plan, how many shows how many ads we run on the show, by the exposure data that we have here. So it's, for example, 1 multiplied by 5 plus 1 multiplied by 6 plus whatever we have here multiplied by the exposure that we get here. Okay, so it's, again, I'm going to use for simplicity and easier the sum product. So that's going to be our decision variable. So I'm going to select this cell, comma, and then the exposure data that we have. And I hit OK, and calculate it 11 million. Okay. So again, if you look here, so it has selected the advertising plan. So this is our absolute value. That means that if I actually drag this down and copy into other rows, it's gonna these values are gonna fix. It's not gonna select the other rows. Okay. So I can actually drag this down, and it's gonna copy the formula down. So if you click on this on the formula bar, you can see the sum product, the advertising plan, which is our decision variable. Just states the fix, but for the data, it actually runs for the second row here. And so we can just copy and paste it in other cells instead of redo it. Let's actually, so what we want to do, we wanted to reach at least these number of views, right? It was the minimum requirement. Okay, so that means in our model or constraints language, these actual exposure should be greater than these values, right? Minimum requirement. Right? So let me actually install a cell here on the left side of this, and then I'm gonna use the symbol here, inequality greater than. So I'm gonna go to the symbol here. I'm gonna use this. I'm gonna copy it for other rows. All right. Right. So now, yeah, it makes sense now. Our actual exposure for this men 18 to 35, it must be greater than the minimum requirement, which is 60 million. For 36 to 55, right now is 8. It should be greater than 60. Right. So this is we are done with the part of the model, but we have to put it in the solver. Right. Any question here before I put it into solver? All right, so we're gonna go to solver, go to data tab, then to analyze group, click on solver. Before we do that, let's actually name our objective function here. So I'm gonna select the objective function. We name actually the decision variable, but we didn't name our objective function. Left column. Also the required exposure. Let's select this one by holding down the control key on Windows. Auto. All right. Okay, so now let's go back to the solver here. Okay, so set the objective. So the objective was to minimize the total cost of our advertising plan. So that's the total cost here. 70. And we wanted to minimize that, so make sure that the minimization here is selected. And by changing variable cells, that's our decision variable, or here our advertising plan. So I'm going to select all these cells here. And then I'm going to add the constraints here. So if you look at this constraint, we're going to have actually 6 constraints here because we have 6 different demographic groups. But because all of these constraints have the same actually inequality sign, all of them are greater than this value. So I can actually just do it in one setting. So I'm gonna pick the greater than equality. And on the cell references, it's going to be on the left-hand side. So I'm gonna select all these 6 cells here. So these values should be greater than or equal to, as you see in the slide. And then on the constraint side, the right side, I'm gonna pick all these right-hand side values, which are the minimum requirements here. I'm gonna click OK. Okay. So right now, you see that we have total cost here. So the range name that we use here is actually up here right now. Our decision variable is the advertising plan. The constraint is the actual exposure. These must be greater than the required exposure. Okay. So that's our constraints. We also had the non-negativity constraint because you can't run negative number of ads on TV, right? So this you must make sure that this is selected. Then we're going to use the simplex LP, so you make sure that simplex LP is selected. So everything is actually ready, and I'm going to run this. Okay, so look for our decision variables here. Just random numbers I have put them here. Okay. So click on solve, and it gives us this message that it has found actually an optimal solution. And I click OK, and it keeps the values. So this is our actually advertising plan. It says no ad for Revenge or on Revenge or Sunday Night Footballs, 8.7 on The Simpsons. This could be actually the average, so that's why you see you don't see the whole numbers here. You see the numbers. 0 shows Homeland, 0 shows on CNN, and our total cost would be 1,870, but this is actually in thousands of dollars. So this would be 1,870,000. Okay, and if you look at the actual exposure, this is our requirement. You see that all of our minimum requirements are met here. For example, the actual exposure for the first demographic group is greater than 60. For the second one is exactly equal to 60. For the third one is more than 60, 28. And for the fourth and fifth one is exactly equal. And for the last one is also. So that's our total cost. Any question here?
I actually have a question. On my like ribbon or toolbar, I don't have the solver function. Is it something you have to add?
Oh, well, we did this, I think week 2. So you have to go to File and go to Options. Do you have a Mac or Windows? Or PC?
Windows.
Okay, so go to Add-ins here, and then for you, it should be in the inactive application. If you don't see it, mine is here because it's already active. So you see the solver add-ins, click on it, and then hit go here. And you're gonna see this window open, and you make sure that the solver add-in is selected, and then click OK. And it should appear on your data tab.
Okay.
Did it work?
Yeah, thank you.
Sure. Okay, so let me see what we had on the lecture. It says the optimal solution is not obvious. Okay, so let's see why the optimal solution is not obvious. We could actually do this little computation. We could actually find the total exposure for each shows. So that would be adding up all these exposure data that we have from Nielsen. So for example, for Revenge, I can sum up these values. 5 million, etc., etc. So for the Revenge shows, for all these demographic groups, total exposure is 21 million. Okay. I can actually drag this down to compute for all these TV shows. So these are our total exposure for each demographic group for each actually shows for all the demographic groups. And then we have also the cost per ad. We can actually find the, let me insert another row here. You can find the cost per exposure. Okay, so cost per exposure. This would be 150 divided by 21. I'm going to compute this for, drag it down for all the shows. Make this a little bit neater by removing the number of decimals here. Right. So we could say, okay, this is the cost per exposure for each TV show. So you might want to, if you look at it, you see that for 2 shows, for The Good Wife, it has the smallest one, and also the next one is actually for this Sunday Night Football. So we could say, okay, so because the cost per exposure for these 2 TV shows actually is smaller than the others, so that means that, okay, so it looks like logical to plan based on these 2 shows. So it seems like a good decision. But if you look at the optimal solution that we got here, actually, the optimal solution is no TV show, no ad to be run on the Sunday Night Football, although it had actually the second smallest cost per exposure. So that's why this is not an obvious actually optimal solution, because it would be obvious if we had, we would have running ads on the Sunday Night Football. Okay. All right, so let me go back. So because it's going to take time for me to go back from the lecture slides to Excel, so I'm just going to read out for you. Okay, so next on the 8th page of the lecture, we have a couple of questions. We actually have 4 questions. The first one asks for, this is related to sensitivity analysis. It says, how much would the cost of SNF ad have to drop before the optimal solution changes? Well, okay, so first of all, let's interpret the question, what it asks us for to do. Right now, if you look at our advertising plan, it says, do not run any ad on the Sunday Night Football. Okay, so the question says, how much? It's because of this cost, right? Because it's pretty expensive. It's $100, right? It's actually the 3rd show. These 2, the Revenge and The Good Wife, was 140, the most expensive ad, and the Sunday Night Football is the 3rd. Okay, so the question asks how much this cost. It would make sense, right? How much should we drop this cost so that it would appear on our advertising plan? So how can we answer this question? Well, we could do some TDS computation by changing these values from 100 up to 0, for example, 1 by 1 to see, when would you have like non-zero ads here in the optimal solution. But this is a question actually related to, if I can get some out of my way, related to sensitivity analysis. Okay, so I'm going to go to the data tab again. I'm going to open up Solver again. Hit on Solve button here. And on the right-hand side, you see we have the reports. Okay, so I'm going to click on the sensitivity analysis tab, and I'm going to click OK. So it would actually generate for me the sensitivity analysis output. So if you look here, it's going to take a little bit for probably, and then it's going to appear on your another sheet here. So you're going to see this sensitivity report. You're going to see actually 2 tables here. Okay, so one is for the decision variables and another one for constraints here. Okay, so we talked about the all these final values, the allowable increase and decrease, and also the objective coefficients last time. What we want to do here, we want to talk about the constraints here. Okay, so right, so and also the reduced cost and the shadow prices. So The question asks for the Sunday night night football. It says how much this costs, which is right now the coefficient in the objective function is $100. That's the per ad cost for this show. How much this cost should actually be reduced so that it would appear on the final solution or optimal solution. Right now it's 0. It's not an optimal solution. Okay? And that's actually a question addressed here. Okay? That's on the reduced cost. So it says that if you actually decrease the cost of this TV show by 7.5, these are in $1,000, then it would appear on our optimal solution. So that's what reduced cost means for these. Okay, and you see that for those shows that are on our actually advertising plan, the reduced cost is 0 because they are already on our advertising plan. Okay. So that's the reduced cost. Reduced cost is for those decision variables that at the optimality, they are not in the decision value. They are actually non-zero, or they actually are 0. How much we actually have to reduce the cost of that if we are dealing with a minimization problem, so that they would appear in our optimal solution. And on the next table, the constraint table, we have 6 constraints. So what actually you see here is, which probably could be new to you, or we actually talked about the shadow prices. So shadow prices are for the resources that they have for maximization, and here also for the requirement that we have, the minimum requirement for each demographic group that we have. So that's, what does it mean? It means that for example, let's answer the second question here, because this is related to the shadow price. Okay. It says, how much would it cost if the GFC would require 1 million more exposure to the woman age 18 to 35? So that's this one. So right now, the final value, that's 60, and the constraint right-hand side is 60. So that means that we have actually exactly meet our requirement. Okay. If they actually wanted to have added actually 1 more million people exposure, how much actually is gonna cost us? Okay. So if you want to do that using the optimization problem, you would have to run another problem here. But the sensitivity report can actually show you here. And this is the shadow price, okay, the interpretation of shadow price. So that's 10. That means that if you add 1 more value to the right-hand side, which is the requirement for the minimum requirement for the show, which is right now 60. So if you increase it to 61 million, you have to pay $10,000 more. Okay, these are the cost. Okay, so the objective function, which are in $1,000. Okay, so it's going to cost up $10,000 more to reach 61 million viewers. Okay. And for each 1 million more viewers, you're going to actually have $10,000 more. Okay, and the allowable increase is actually 11. Okay, so right now it's 60, and this decision variable is the optimal solution is not going to change up to 11. So right now is 60, so up to 71 million viewers. This is not going to change, and each million viewer is going to cost 10,000 more. All right, next question. How much would be saved if the GFC required 5 million fewer exposure to the men range 36 to 55? 36 to 55. Okay. So the final value, the optimal solution here is 60 actually million. And the constraint was 60 million as well. So that means that we have actually meet our requirement. Okay. So the question asks, if we require 5 million fewer, that means that if we drop this 60 to 55, how much the cost will actually reduce? Okay. So to answer this question, we can actually go back to the data or to our model, and we can change these values here. 60 here, man, woman 835, man, this would be this one. So we could actually change this from 60 to 55 and then rerun the model, or we can go to the sensitivity report and answer it from here. Okay, so that's for shadow prices as well. Okay, so for each 1 million or one value here, for each one additional value or less value, it's going to cost us increase or decrease by 15. Okay, so if you reduce this 60 from 60 to 55, that's 5. It would be, the cost would drop by 5 multiplied by 15. Okay, so that would be 50 and 25, $75,000. Okay, so if you reduce the number of required viewers for this men 36 to 55, you're gonna get $75,000 viewer cost. Okay. All right. Any question regarding these two concepts, the reduced cost and the shadow price? Right. So let's go back to the model again. So what we have here on our optimal advertising plan, we have, for example, 8.7 or 8.72 ads per distro, which is The Simpsons. Okay? And one way that I interpret this was to, this is like the average. Okay, so that's why we get 8.7 or 8.72. But it really, if just as a one value, it doesn't make sense because you cannot run 8.7 ads on a TV show, right? So we could actually add another constraints here to make sure that our ad plan are all integer values or whole numbers. Okay, they don't have any 0.31, etc., etc. Okay, so I'm gonna to do that, I'm gonna go to the model on Solver, and then I'm gonna add these constraints. I'm gonna tell Solver or to consider this constraint that all of these decision variable, which is our advertising plan, they must be actually integer. Okay, so this is how you would do it. I'm gonna add another constraints here. And I'm gonna say all of these must be from this integer. Okay, I'm gonna add it to the constraint. So you see that this actually appeared here. It says all of the advertising plan decision variable, they must be integer values. Okay? Let me actually keep this solution that we have here. Must be simple. I want to keep this the solution that we have right now, and I'm going to call it continuous. And so this new one, I want the optimal solution to be all integer values. Okay. And this is our total cost when we have total cost for continuous solution. Which was 18.17. Right, so let's read on the model. This is total cost, and I added these integer values. I'm going to hit run, solve it. And as you see here, our decision variable or the optimal integer advertising plan actually has changed. Also, the total cost has changed. I'm going to keep this. Okay, before I do that, if you look at the report side on the right side, you don't see actually the sensitivity analysis. Okay, because the sensitivity analysis is only when you have continuous decision variable. by adding these decision variable to be integer, you're gonna lose actually that report. So if you look at our optimal ad plan, you see that all of these values actually are integer values. We don't have any, 0.34, etc., etc. And also our total cost has actually is increased by $10,000. So that's what to do about non-integer results, which was another question. Okay, so let me see what we have. Okay. All right. Okay, so let's do another approach here. You want to see how can one maximize the total number of exposures beyond the minimum requirement. So right now we have, it must be greater than 60 million for each demographic group, or for 28 million for some demographic group. So we want to see how we can maximize the total number of exposure beyond the minimum required, subject to a budget constraint on total advertising costs. For example, we didn't have any budget here. So what would happen if we enforce a budget? For example, we said that, okay, our advertising budget is, it should be 2 million. So we cannot, use more than that. So let's see how we can formulate this one. I'm going to go back to the advertising. All right. So right now, this is our optimal solution, and it's going to cost us $1,880. These are in $1,000. I'm going to compute in this cell here. I'm going to compute the extra exposure. And here I'm going to compute how much we have gone overboard. That means more than the requirement, minimum requirement that we have. So here the actual exposure that we have in this solution is 71. We're going to subtract it by the minimum requirement, and we're going to get 11. Then I'm going to drag this down so that we compute it for other range group as well. Let me center this. Okay. So, and also we have to actually enforce a budget here too. Okay. So we would have to actually, this is another model. It's going to be another model. So you can actually save it as, save the model right now as, say, the advertising done. Browse. Okay, so I want to enforce the budget. So we have computed the total cost here. This total cost is going to be actually not going to be our output anymore. It's going to be a calculation. And here I'm going to put the budget. Budget is 2 million. So 2 million, because these values are in thousands. So the budget would be in 2000 is 2 million in 2000. I'm going to call this budget. I'm going to use the range name here. So we want to make sure that this is less than equal to our budget. The total cost of our advertising plan is less than our budget. And because this is no longer our output, I'm going to use the mod calculation part. Okay, right. So the model is going to change. This is going to be another actually constraints. It's going to be the total cost of our plan, whatever plan we have, must be less than equal to $2,000 to $2 million, which is going to be our budget. Right? And then we wanted to maximize the exposure that we had over the minimum exposure that we have. So we want to maximize the total number of exposure beyond the minimum requirement. Okay, so these are beyond the requirement that we have. Okay, and these are for each range group, and I'm going to find the total of these. Okay, total exposure. And I'm going to compute the sum of these values. So this is going to be our actually output that we want to maximize. Okay? We want to maximize the total number of exposure beyond the minimum requirement. So I'm going to use the team for output. Okay, so we have to maximize this. I have a lot of windows open here, so that's I've used up my RAM. Okay, so right now with this plan that we have is $18.8 thousand, or these are actually million viewers, so this would be 18.8 million. So what we want to do is we want to maximize this total extra exposure over the requirement, that minimum requirement that we have, considering that we have only 2 million budget. So how do we have to formulate this one? So it's going to change our constraints, and it's going to change our objective value. So our objective value is no longer going to be total cost. It's going to be total exposure. We want to maximize this. Okay, so I'm going to click on maximization. And what is our decision variable? It is still our advertising plan. Okay, so I'm going to keep this here. We want to make sure that the actual exposure, this is actually met. That means that we're going to have our minimum requirement for each age group, demographic group meet. And then I want to make sure also the advertising plan are also integer. So that's also correct. And we have to add another constraint. Remember the budget. So I'm going to add the constraint here, budget constraint, and this should be less than equal to the budget, which is 2,000 or 2 million. I'm going to add this one. And the non-negativity constraint, this must be also selected, simple XLP, and then I'm going to click on the stop. So see what happens. Okay, so the total extra exposure over the minimum requirement, beyond the minimum requirement that we have, is 41.2, and we have actually used up all the budget, 2 million budget, and this is our decision variable. Okay, this is our actually optimal ad plan. Okay. So we have met all these ad exposure to these demographic groups, and we have maximized the exposure beyond our minimum requirement, considering that we had only $2,000 budget. All right. So we went with 2,000 here, which is these values again. The costs are in millions. So it's $2 million budget. Okay, so the next question is, it says use the solver table, and so see. Let me show the slide with you. It says, how sensitive is the solution to the total budget over the range of between 1.7 million to 2.4 million? So this is, if you remember, this is like a data table that we used. But because we are using optimization, as I showed you how to use the solver table add-in, we install actually an add-in called solver table here. So we're going to actually do this problem in solver table. Okay. So what we want to do, okay, I think you're not seeing my Excel. Let me share the Excel file. All right, so the solver table that I showed you how to install as an add-ins, this is going to help us to answer these types of questions, which is going to be by changing one inputs, giving the range of numbers, how it would affect an output, several outputs. Okay, so this is a question that we can answer using the solver table. Okay, so right now the question asks, what if actually we change the budget, for example, from 1.7 million up to 2.4 million? How would that change our, optimal advertising plan and also our total exposure? Okay, so I'm going to open up the solver table here. I'm going to go to run solver. This is a one-way table. And this is where what actually cell you want to change. Okay, so we want to change the budget. Okay, so this is going to be our budget. We want to change it. By the way, this should be actually in this thing. Let me go back and do that. This is an input, so this should be in. Right. Open number 10. Run solver table. You want to select budgets, and we want to change it from 1.7, so that would be 1,700. Make sure that you don't make a mistake. 1,700. The maximum value is 2,400. That's 2.4 million, and by say 100. Okay. What are the output that we want to see the impact of these changes on? We want to see the impact on our decision variable or advertising plan. So I'm going to select these, and I'm going to hold the control key and Windows down, and I'm going to select also the total exposure. Okay. After I do that, I can just click OK. And what's going to happen is, if you remember from last week, it's going to open a new sheet here, and it's going to open all the changes for these range of data that we have. So it might actually, it's going to do a lot of calculation and re-optimization and rerunning the model. So it may actually take more time. For you, it could be different depending on your system. So this is what we get this new sheet appeared here. And it's a one-way analysis for solver modeling data worksheet. These are the budget constraints and the budgets and the range of values that we have from $1.7 million up to $2.4 million. And we get our decision variables. These are, our optimal ad plan for each different TV shows. We had, remember that we had 8 different TV shows. So unfortunately, we can't get it to show us the name of the program here. So it just show it by numbers, 6, 7, 8, etc., etc. And also we wanted to see the impact of these changing budget on the total exposure. So the last column shows for these different ranges here. Another component that you see here is the graph for each of these outputs. Okay, so if you click on this, right now this is for advertising plan 1, which was actually our first show. We go back to this, it should be for Revenge. Okay, so the first one is Revenge, then the SNF, the Simpsons, the Sports Center, etc., etc. Okay, so instead of using the name, it's going to use advertising plan 1, 2, 3, etc., etc. So you can actually, by selecting from this list here, you can see the impact of the budget on each, our optimal plan of adding running ad on a specific TV show. For example, this is for number 5 TV show, which was 1, 2, 3, 4, 5 Homeland. Okay. And also you can go use it for the total exposure. So for total exposure, as you see here, it automatically is going to plot for you this neat graph. So on the x-axis, you see the budget. It changes from $1.7 million up to $2.4 million. And it shows the total exposure on the y-axis here, which ranges from 0 up to 120 million. So as you see here, for 1700 and 1800, it says non-feasible. That means that with this, if you have a budget of $1.7 million or $1.8 million, you cannot actually get to feasible solution. And that means that you cannot find any TV ad plan that would reach your minimum requirement audience exposure that you wanted. Just remember the $60 million for men 18 to 35, $60 million for 36 to 55, etc. So it says that if your budget is 1.7 million or 1.8 million, you cannot reach that minimum requirement. Okay, so you need at least $1.9 million to reach your minimum requirement for the audience exposure that you have. Okay? So that's why you see that these are zeros from 1700 and 1800. The exposure is 0 because it's not feasible. The exposure is actually 0. From 1900, you see that you have actually a feasible solution, and your total exposure actually is going to grow as your budget grows. So as your budget grows on the x-axis, you see here, the total exposure almost linearly increases. So this is how we can actually answer this question. The question was, how sensitive is the solution to the total budget over the range of 1.7 million up to 2.4 million? All right, hello everyone, welcome back. So the next question was any flaw on the concept of the way that we model it or approach the model or the problem here. Let me share the model again with you. So this is the latest model that we had for the budget and the maximum total exposure, given that we want to reach this minimum requirement of exposure to these audiences, these demographic audiences given a budget constraint. Okay. And actually the flaw here is the assumption that there is a linear relationship between the number of viewers that we would reach and the number of times that we actually run an ads on a program. For example, here we have 6 ads run on Simpsons, and in our computation, we're gonna multiply 6 by the 5 million audience, which is 5 here, reach for the demographic range of men between 18 to 35. But the problem with this logic is that it's not really true in practice, because generally there are the same people most of the time who watch the same TV show. So we have, for example, Simpson fans, which each time that the TV show runs, they are the same people who are watching. Like I don't know, I don't have a number, but say 70–80% of people who are watching, they're the same, right? So you're not gonna reach 6 times more than that, right? 6 multiplied by 5 million, they're the same, right? So it should be basically, it shouldn't be a linear relationship between the number of ads run multiplied by the viewer exposure. Okay, so this is one of the major flaw of this problem that we approach. It's not only the model, this is actually how we perceive the problem. We made an assumption here that you can actually reach this audience each time that you run the ads. But the next time that you run the ads, probably the same people are viewing the ads. So you're not, reaching new viewers. Okay, so that's one of the major flaws here. Okay, and the resolution to this is to, instead of making this assumption of linear relationship between the number of times that you run an ad on a TV program and the viewers that you can reach, instead of this linear assumption, we should assume a nonlinear relationship. So, for example, the first time that you run an ad on Simpsons, say, for example, you can reach about 5 million people in the range of men 18 to 35. The next time that you run the ad, it's not going to be 5 million again. It's going to be, some of them are going to be the same people. Maybe there are some people, say 1 more million people, or it's going to be, for example, 3 million people that are viewing the ad for the first time. And also, if you run the ad for the same person multiple times, maybe it doesn't have added value, or maybe maybe the first time it's enough. Okay? So that's the flaw here, and the resolution or the problem with it is the linear relationship that we make the assumption for. Okay. All right, so this is the third part. So we're going to see some additional problems here. There are different applications here. So, we studied with if you remember, our first optimization problem was investment plan on 2 stock, for example, A and B, and then we had a diet problem. And as you see here, there are different applications of optimization here. So we're going to see 2 more applications here. And in the textbook, you can see different examples of different applications which you can find optimization for. So chapter 4 presents 7 different applications for linear programming. We focus here on 2 examples that are in the service part, not in operation, not in manufacturing part. So we're going to see 2 examples for scheduling here. Okay, so scheduling of the staff, which is it can apply for the service, not for those businesses that manufacture something, or say anything that does business, does services, for example, for planes, for trains, for those kind of things, or for banks, or for telephones. Okay, so the first problem, employee scheduling. Okay, so let's go on the first problem, which is in the service part, and it's actually very popular, and that's employee scheduling. Okay, in many businesses, employees work specific shifts within a given day, or are scheduled to work on particular days, or specific days, say 5 days out of 7 days a week, over the course of a week or a month. So as a sake of this example, consider a business that requires a different number of full-time employees. So FTE stands for full-time employees. So we're considering like a weekly schedule here, and say this business want to have 17 full-time employees on Monday. On Tuesday, the load of service or customers is lower, so they don't need 17, they need actually 13. On Wednesday, they need 15. On Thursday, they need 19. So that's the busiest day. And on Friday, Sunday, and Saturday and Sunday, you see the 14 and 16 and 11. So on the weekend, Sunday, they need actually the fewest. Right. So what we want to do, the key role is each full-time employee works 5 consecutive days, right? And then gets 2 days off in a week. And the goal is find the fewest number of full-time employees that would actually meet or exceed this requirement that we have here. So one simple, intuitive solution to this problem would be to hire 19 full-time employees. That would meet the maximum requirement on which is on Thursday, but on other days you're gonna have a lot of employees that are not needed. Okay, so this is what we want to do. We want to find the fewest number of full-time employees needed to cover these minimum daily requirements. All right, so we want to model this problem. Let's approach the problem. What is our decision variable? We want to see the number of employees that would start working each day, because we have 7 days per week, and each employee would work 5 consecutive days from the day that it starts working. So that means that we have actually employees who work on the weekend. Okay, so if an employee start working on Monday, he or she's going to work on Monday, Tuesday, Wednesday, and Thursday and Friday. Okay? It's going to be off on Saturday and Sunday, and again, so on and so forth. Okay, so you want to see, this is your decision variables. How many employees to schedule on, say, Monday, start working on Monday, another for Tuesday, another decision variable for Wednesday, Thursday, Friday, Saturday, and Sunday. So we're going to have 7 days a week. So we're going to have 7 decision variable. We're going to actually name our decision variable based on these days of the week. So Monday, Tuesday, Wednesday, Friday, Saturday, and Sunday. What is the objective? We want to minimize the number of employees, full-time employees that we would need. Okay. Otherwise, you can actually do the maximum, which is 19. And what are the constraints? The constraints is clear. We had the numbers here, our inputs. We need to have 17 employees available on Monday, 13 on Tuesday, 15 on Wednesday, etc., etc. Right. Because the 5 consecutive days of work rule, this actually makes the problem a little bit complicated. So we need to set it in a way that we can model it. Okay, so let me open up the Excel file. Let me close all of these. Save. So that's advertising data. Calls into employee schedule. Employee scheduling. So it's gonna take a little time to, if this one is filled out, I have to find. Sorry, I don't have one. All right. So this is what I'm gonna do. I'm gonna open up a new Excel file and create it from scratch. Okay. Let me share this with you. Okay, so this is, I'm gonna build it from scratch. So I'm gonna call it model employee scheduling. Employee model is fine because I can write the name of the problem here. Employee scheduling. All right, so I have to copy a paste models here, then I'm gonna show it to you. All right, let me get rid of these. Okay, so we have listed here the number of days we have on the rows and columns here. So Monday, Tuesday, Wednesday, Thursday, Friday, 7 days a week. And these are actually going to be our decision variable on Monday, Tuesday, Wednesday, Thursdays, because our decision variable is how many employees should start working on Monday. Right now, it's for Monday is 2. That means that 2 employees start working on Monday. Right? These are just random numbers I have given them here. Okay, so I can do, for example, 1, 2, 3, 4, 5 random numbers. 4. And this is going to be because each employee only worked 5 consecutive days. So if someone start working on Monday you're gonna have that person working, so 1 person working. So it's going to be this one working. I'm going to use the absolute value set here. F4. So F4 is going to give you the absolute value here. And then I'm going to drag it down up to Friday. Okay, Monday, Wednesday, Tuesday, and Friday. All right. On Tuesday, if someone start working on Tuesday, then you're going to have that many people start working on Tuesday. So I'm going to make it equal to this cell value. And I'm going to use the absolute cell, which is F4 in Windows. Okay, so as you see here, it used $sign, double $sign. So it's going to make that fixed, so I can drag it down and it doesn't move. So 2 people start working on Tuesday. They're going to work consecutively until Saturday. Okay. 3 people are start working on Wednesday. So on Wednesday, you're going to have 3 people. So I'm going to select this cell equal to that cell because I want to drag it down. I'm going to make it absolute. So I'm going to click on F4 and then I'm going to drag this down. So someone who worked on Wednesday, start working on Wednesday, it's going to work up to Sunday, and on Monday and Tuesday, going to be off. For Thursday, we're going to have 5 people. I'm going to make it absolute cell value. And I'm going to copy it here up to Sunday. Also, I'm going to copy it on Monday too. 5 days, right? So they're going to have Tuesday and Wednesday off. And for Friday, they're going to have 1 people on Friday. I'm going to use the absolute cell again. I'm going to copy it down to Sunday and also Monday and Tuesday. Okay. And for Saturday, we have 2 people that start working. I'm going to use absolute value, absolute cell. And I'm going to copy it on Monday, Tuesday, and Wednesday. Okay. So for Sunday, I'm going to put it to this value, and I'm going to use absolute cell reference. I'm going to drag it down here, and also on Sunday. All right. So now if I actually change these values, these are going to change. So for example, if we set to 5 people to start working on Monday, I'm gonna have 5 people on Monday to work. All right. So this is going to be our decision variable. All right. So these are random numbers, right? So we have to find the optimal solution. So what else do we need? We need to add the inputs that we have. What are the inputs? The employee requirements. So I'm gonna add it here. Employee requirements. All right. So we need to have at least 17 for Monday. That was over 17 for Monday, 13 for Tuesday, 15 for Wednesday, 19 for Thursday, 14 for Friday, 16 for Saturday, and 11 for Sunday. So these are going to be our inputs. I'm going to have to measure style because this is a new Excel file. Input, I'm gonna center, making alignment center. All right, good to go. Okay, employee requirement. So what else do we need? Okay, so we need to actually for each day, because we need to find how many people are working on that. For example, people who have started working on Monday, they're working on Monday. And people who have started also on Thursday, they're also working on Monday. People who have started working on Friday, they also work on Monday. So if you just find the summation of these cells, it's gonna tell you the total people who are working on Monday. Okay, so I'm going to make another cell here. It's another column here. I'm gonna call it the number of employees working. Okay, employees working. Not okay, employees working, number of employees. All right. Okay, so a summation of these values. So I'm gonna select all these cells, click OK, and then I can actually drag this down so it would actually compute all the values for me for all the days that we have in the week. All right, I'm gonna insert another cell here. So what we want is we want these employees, the number of employees working on Monday, we want to be 17, at least 17, right? So this must be greater than or equal to. I'm going to go to insert and then symbol. I'm going to select the greater than or equal to. This is just for presentation. It's not going to do anything for our model, right? All right. So now I can copy this and paste it down, drag it down here. So this says that all of the employees working on Monday, they must be greater. The total number of working on Monday, it must be greater than 17 or 17 for Tuesday, 13, etc., etc. Okay. All right. So this is going to be our constraints, and so we have our decision variable, our constraints, and also we need to set our objective function. What is our objective function? We want to minimize the number of employees who are working. So let's do that here. I'm going to call this the total employees. Okay, great. So this is going to be equal to the summation of these cells. Sum of these cells. And this is going to be our output, right? So I'm gonna use the output, my output theme or format. Now centralize it, find its center, right? Okay, good. So it looks like we have everything here. Now we can actually try to model it in Solver. So let's do that. I'm gonna go to data, open up the Solver, and this is going to be, we can also name our range names here. So I'm gonna do that. Formulas, create from selection, I'm going to name that one, and I'm going to name these two as well. I'm going to place that one down here. So now I can select these cells, hold the Control key on Windows, and then select Seed Cells, go into Formulas, Create from Selection, and then top row, make sure that's selected, then click OK. And now we can actually see the name ranges that we have here. We have the requirement, that's the employee requirement for each day. The total employees, that's our output or objective function. And then the employees working. All right, now we are good to go. We're going to go to Data, Solver tab, open up the solver. This is going to be our output or objective function, which is going to be the total employees. So right now it just shows C17, but when you actually run it or when you add the constraints, it's going to actually show its range names. We are minimizing or maximizing. We are minimizing, select the minimization. In the change in value variables, that's actually our decision variable. So I'm going to select the range of decision variable right now. It has random numbers. Again, it doesn't show it here. Oh, I forgot actually to do that. I'm going to use the range name for this as well. Okay, good. All right, so now it should show it in name for it. Okay, good. As you see here, the number is starting, number of employees starting. That's do that. Change the directives. Okay, now it's good. All right, so as I said, probably 2 weeks ago, the first version of whatever modeling that you do is not your final. It shouldn't be your final version. You should have like a couple of in the middle that you would design it to throw it away and come up with the last version, which is the best version. So that's you have to do all this addition and division here. So we added the decision variable. Now I'm going to add the constraints here. The constraints, we're going to have 7 constraints here for each day, minimum requirement for staff. Because all the constraints requirement for each day have greater than equality, that means they are the same kind of inequality. So I can actually just select all of them at once. So I want these cells to be greater than or equal to these cells. Okay. So if I click add, okay, it's going to add them. All right. All right. So let me select simplex algorithm, make sure that this is selected because you cannot employ negative number of employees. Okay, so everything is checked. Now click OK. It's going to solve it. All right, so let's see what happened. Well, it says on Monday we should have 1.333 people that start working. So as you see, all of our, except for the on Sunday and Wednesday, every other day we have actually on Monday, Tuesday, Thursday, and Saturday we have non-integer values, and that doesn't really kind of make sense. You cannot have 1.3 or 7.3 or 3.3 number of employees. It's people. You cannot divide them. And the total employees 22.3. Again, it doesn't make sense because we are working with people. It's not a resource that is divisible. Okay. So what should we add here, or what should we do here? We should actually add another constraint, say that these decision variables, which is our number of employees, they should be integer values. Okay, so let's go back to Solver, and I'm going to add that constraint here. I'm going to tell it that all of these employees that start working on each day, they must be integer. Okay, now hit OK. It's going to appear here. It says number of employees starting, it should be integer. I don't have to touch anything else. Then I'm going to click OK. All right. So as you see here, all of the constraints, the integrality constraint has been enforced. Now our solution makes sense. It says that the optimal scheduling plan is to have 2 people start working on Monday, 3 on Tuesday, 3 on Wednesday, 7 on Thursday, none on Friday, 4 on Saturday, and 4 on Sunday. And you need a total of 23 to meet this employee requirement for each day. If you look at the employees working, on Monday, you have exactly the same number that you would have expected or wanted, 17. On Tuesday, you have exactly the same. On Wednesday, you have actually 1 extra employee working. On Thursday, you have exactly 19 that you needed. On Friday, you have extra employee. Saturday, the same. And on Sunday, you have more than 7 extra employee working. But this is the best schedule that would meet or exceed this requirement and would minimize the total of employees. If you get a different solution, if you tried this and you got different solution here, it is possible to have different, by solution means the decision variables or a schedule. If you get, for example, different values that you see here, but you have to, you should get actually the same number of total employees. Your objective value should be the same, but you could get different number of employees here, and also different kind of setting here with the same 23 number of employees that I got, because this problem has actually multiple optimal solutions that's possible to have in position. That's a more advanced than this course that we talked about it, but it's possible that we do that. But so you could have a scenario which you have multiple optimal solution, but in those optimal solution, your objective value is going to stay the same, but your decision variable may actually vary, right? So you could have multiple optimal solution with different schedule, but the same objective value. Okay. All right, so the first thing is non-integer versus integrality. We saw that. Sensitivity analysis. We can't actually do sensitivity analysis for this example because, as I said, if you remember, when you have an integer problem that your decision variable has to be integer values, on the report size, you don't get a sensitivity analysis report. So whatever sensitivity analysis you want to do, you have to do it actually manually. And so that's when you don't have a linear program. Let me share this the lecture with you. So we want to see, we saw the impact of non-integer model versus the integer model. As you saw, the non-integer model actually had a smaller objective value. Okay, where was I? But the solution did kind of make sense because it's people. You cannot divide them. You cannot have a decimal number like 1.33 people start working on a Monday. Okay, so that's the difference. All right, so it makes sense in reality to study this problem or model this problem as integer programming, not linear programming. It's actually a linear programming, but it's integer linear programming. All right, so let's see the sensitivity analysis while we don't have the luxury of the sensitivity report. We want to see how do the employee requirements influence the total number of employees needed. Okay. What does this say? It says, for example, what if instead of 17, 13, 15, 19, whatever, oh, you don't see this value. Let me share this. All right. So the question asks for, in this problem, this minimum requirement for each day, what if instead of 17, it was 18? Okay. What if it was 14 for Tuesday? What if it was 16 for Wednesday, etc., etc. Okay. So we want to do sensitivity analysis, right, for different values of this requirement. What would happen to our number of employees, total number of employees? Okay. This is the kind of like analysis, what if scenarios that we want to do. Okay. So what should we do to kind of be able to answer this question without having to run multiple tedious kind of work to do? Okay. We can actually keep this problem as it is, but set another input as like the extra requirement. You would actually add that extra requirement on this set of employee requirements. So for example, we can add, I'm gonna add, for example, another value here, extra requirement. Right. Extra requirement, and I want to make it as an input. So I'm going to use my input, say 1, or it could be 0 or whatever. Okay. And we have to actually add a new set here. So I'm going to insert a new column here. It says the new employee requirement. New employee requirement. Okay. Now, instead of this, instead of 17, I want it to be 17 plus 1, or whatever value is in the extra. So first of all, because I want to copy and paste it, I'm going to use the range name. So I'm going to use the formula create, right? So now I named the this cell, input cell, as extra requirement. Now I'm going to say this cell for Monday, it has to be 17 plus whatever value extra would want to have. And I can now drag this down and put it here. Okay, so this is going to be my right-hand side now. If I change this to say 2, all of these values are going to change. Okay, so now by just this one value, I can actually run different problems to see the impact on. Okay? And you can use actually using the solver table to do that. Okay? So this is a good way of doing it. The solver table, it has to be just actually one set. Okay? Right. So let's do that. You want to see the impact of this on extra requirement for each day, on our decision variable, which was our how many people start booking on Monday, etc., and also on the total employees required. Okay, so let's run a one-way table. Run one-way table. So the input cell is this one, which is the extra requirement. And the minimum value for it, say it's 0, that means that the same as what we had originally. And then we're going to add it with an increment of 1 up to, say, 6 for incremental 1. Okay. What are the output that we want to see the impact on? The schedule which is how many people start working on Monday, Tuesday, etc., and also the total of employee that required. So I'm gonna hold the control key down and I'm gonna select this cell, right? So it can look good. I'm gonna click OK. And if you look here, it's gonna do a lot of computation. It's gonna create another sheet here. It's called SSTS1. Let me make this bigger. It's only on my way. All right, so you see the extra requirement here, from 0 up to 6. And for the number of employees starting on Monday, Tuesday, Thursday, Wednesday, Thursday, Friday, Saturday, Sunday. And this is the total number of employees. These 7 days that we have, we scheduled for 7 days, and also the total number of employees that we needed. And with the extra from 0 up to 6, 0 is going to be the same problem that we solved up to 6, right? So now we can actually see better using the graph here. So let's see, for example, on the total number of employees. And the total number of employees, this is the graph. It shouldn't be fair. All right, so there's something wrong here. Let me see. Let me go back to the top machine. Watch to music to screen define. Right, so let me see what's wrong with this. The solver, total employees here. Do you want to minimize this? Right. And number of employees integer. The working must be greater than or equal to requirement. Let's see if this is actually applied. Right, this might be the problem. Let me see. We're gonna go to the formula, open up the name change for extra requirements, input value, number of employees, output address, output value, requirements. So we may need to redo this. Let me go to the model again. Solver, I'm going to delete this and add it again. Okay. Add that these values must be greater than equal to these values. Okay. I'm going to click OK. So that one was added. And click on options, make sure that this, okay, so integer optimality should be 0. I'm gonna click OK. Click solve. All right. So now I can actually go back to the solver table. I think we have to do it again. Oh no, they are here. All right, good. All right. Let's see. I want to make sure that these are all correct. That's N19 and 19. That's true. This might be 0 to 6. That's correct. And these cells are correct too. Oh, good to go. All right. So let's try it again. All right. Let's do. All right. Now it's better. Okay. Total 100. Okay. So on the x-axis, you see the extra requirement from 0, which is the same original model that we run, and you add 1, 2, 3 up to 6. And because this is integer program, it's going to be a little bit up and down, not exactly linear, but as you see, the relationship is almost linear. There is some up here, you know, some division here. but on average, you can see it's almost linear. If this was a linear programming, it would be exactly like a flat line. Right? So what this says, it says that, okay, if you add the same number of requirements on your daily schedule requirement, the total number of employees that you need is going to also increase linearly, right, as you did here. So 1, 2, almost like a linear line is going to go add up. And you could also see the impact that these additional requirement has on the employees, our schedule, which is how many employees work on each day. For example, let's go on Monday. This is the impact that has on Monday. So as you see, it's not exactly like a flat line, right? So for example, if you add 1 or 2, it's going to stay the same, which is 2 people is going to start working on Monday. If you add another requirement, 3, it's going to tell you, okay, 3 people must start on Monday. And for 4 and 5, it's going to stay the same. If you ask it a 6 people requirement, additional requirement, which is 17 plus 6, which is 23, it's going to go to 4. It means that your optimal solution is, your optimal schedule is to have 4 people work on Monday. You can see it for other days as well. This is for Tuesday, for example. This is interesting. It's going to go up and down. For Wednesday. So this is kind of unintuitive, because as you see, for a couple of days, it's going to go up and down. Well, nobody was actually, our solution was working on Friday, so it's going to stay the same. Nobody is scheduled to work on Friday. It's not needed. Right. Okay, so that's that. That was our sensitivity analysis. As you see here, for these types of problem that you have an integer program, you don't have the luxury of using the sensitivity report to answer these types of questions. So you have to do like data table analysis, one-way data table analysis. Going back to the lecture. So we saw that one. How do the employee requirement influence the total number of employees needed? Modify the model slightly so that the minimum staff requirement will have X added to them. So we use that one. Use solver table to do that from 0 to 6. That one as well. Okay, so we're gonna see another extension, not an extension, a similar problem, but a more practical problem, which is closer to the reality, staffing a call center. Okay, so call center managers is going to be a same type of problem. We are going to have a scheduling problem. We want to have people working on daily basis, but we're going to have, instead of like, daily shift or weekly shift, we're going to have day shift based on half an hour time periods. Okay. So call center managers usually plan out how many agents are on duty every half an hour of the day, starting from 6 a.m. up to 9 p.m. And there are 30 half an hour periods from 6 a.m. to 9 p.m. Because there's going to be 15 hours from 6 a.m. to 6 p.m. That's going to be 12. 7, 8, and 9, that's going to be 3 more. So it's going to be 15 hours difference. If you multiply it by 2, because you have 2 half an hour and an hour, you're going to get 30 time slots. Okay? So 30 half an hour time periods. There are 14 possible shifts. If you assume that each worker or employee work 8 hours a day, okay? Because it's going to be, for example, from 6 a.m. up to 2 p.m. So from 2 p.m. to 9 p.m. you're going to have 3, 4, 5, 6, 7, 8, 9. That's 7 hours, 7 hours multiplied by 2 because of this half an hour or 30 minutes shift, you're going to have 14 actually possible shifts. Okay. Right. Given a fixed number of agents, how many should be assigned to work each of the 14 shifts? So this is kind of similar. It asks how much, instead of like having Monday and Tuesday like days of weeks, here we have shifts of a day. For example, from 6 a.m. to 6:30 a.m. and the shifts are half an hour. So 6 a.m. to 6:30, 6:30 to 7 a.m., 7 to 7:30, so on and so forth. What is the objective? Our objective is similar to what we had before in the previous problem, which is to minimize the total amount of, oh no, it's actually different. So we want to minimize the total amount of over and under staffing that we have in our schedule. So this is what we want to do. We want to minimize the number of over and under staffing. So if any of the shifts you have more than what you needed, and in some other shift you have less than what you really needed, you add up these differences, and then you want to minimize the summation of this. This is what we want to do. Okay, so we want to minimize the under and over staffing, the total number of over and under staffing. Right. So if you want to formulate this as a mathematical programming, this is going to be our objective function. Our objective function is going to be the under and or minimizing the total number of over and under staffing. So if CI is the agents available in period number I, that's the number of employees available in time period I, and DI is the requirement, the employee required at that time period, then the absolute value of CI minus DI, if it's positive, it's going to be overstaffing. If it's negative, it's going to be understaffing, right? So that's why we use the absolute value. We want to minimize the absolute value, okay? So we want to minimize the total under and overstaffing in our schedule. Right? Due to the absolute value size, because our objective function have it's in absolute value, that's actually make our model to be non-linear. So far, we have had only linear problems. Okay, even if we had like integer integrality constraints, that means our decision variable, we enforce them to be, instead of continuous, to be integer. The problem was actually in linear. That means that the f of x in objective function and also g of x in the constraints, all of them, the relationship was linear. But having this absolute value makes our problem non-linear. Okay, so this is different type of optimization problems that we haven't had before. Okay? So that means that we cannot actually use the simplex algorithm to solve this problem. We have to use other type of solvers. Okay, so here we're going to use the GRG non-linear solver to do that. Okay? Right, I'm not going to talk about the more realistic version of this. I'm going to go actually and try to model this problem. Let me close the Excel. I have too many Excel sheets open here. Let me close them. They are using up my RAM. Let's open up a new one. Okay. So this is actually a kind of practical problem that we might see at some service work. For example, as I mentioned, travel agencies or telephone agencies. Answer to customers. Right. So because this actually has a lot of inputs, I'm going to use the original Excel file here. Otherwise, it's going to take forever to put all the inputs here. Staffing. All right. This is how it looks like. Hopefully you can see this. It's almost like the concept is the same. It's a scheduling employees, but our shifts are not going to be like 5 days a week. It's going to be half an hour periods per day, like in a day, and our our working days start from 6 a.m. up to 9 p.m. Okay? So since we have 14 shifts, okay, we have 14 shifts. That's why we're going to have actually 14 decision variables, right? So here is going to be, how many people are going to start at the first shift, this second shift, the third shift, etc., etc. And these are going to be our time for half an hour time periods. Okay, starting from 6 a.m. to 6:30 p.m. Half an hour is going to be one period. Then 6:30 to 7 a.m. is going to be the second period. So we're going to have a total of 30 time periods, as you see here. And given that each employee is going to work 8 hours, we assume that they're going to take like a half an hour break between their work to eat lunch or do whatever. We assume they're going to have like half an hour break in the middle. So someone who will start working at 6 a.m., they're going to continue working for 4 hours. So it's going to be 4 multiplied by 2, half an hour is going to be 8. And in the next half an hour, they're going to take a break. Okay. So if you have 2 people at the first shift working, you're going to have them working from 6 a.m. up to 10 a.m. That's from 10 to 10:30. They're going to take a half an hour break. So you're going to have 0 people working. Then starting from 10:30 to 11 and on and so forth, you're going to have them working for another 4 hours. And after that, no, they're not going to work. Okay? The 8-hour shift is complete. If you have 3 people, for example, start working on the second shift, which starts at 6:30, so you're going to have 3 people at 6:30 to 7 a.m. Then the next period up to after they work for 4 hours, they're going to take a half an hour break, and then after that they're going to continue working for another 4 hours, right? And so on and so forth, as you see here. So these values are actually said to be equal to these values right here. Okay. So it's the same values. So if I change these values, my values down there is going to change as well. Okay, all right. So a lot of numbers here. All right. So what else do we need to do? We need to have our demands, right? That's one of the inputs. So these are the demands. We have 30 demands for the 30 time period that we have. For example, from 6 to 6:30, we need to have 8 staff available. 6:30 to 7 a.m., we're going to have 11, and so on and so forth. Okay. So this is our demand. Then we need to also compute based on whatever scheduling plan we went with. We need to compute how many people are working at at a specific shift. For example, for the shift of 6 a.m. to 6:30, if you assign just only one people is going to work at that shift. Okay? So this cell or this column is going to be that value. It's going to be the total number of staff that are working at that specific time period. So it's going to be the summation of all these cells here. Okay. So for example, 21 is the summation of those people who have started working at 6:30, 6:30, 7, 7:30, 8, 8:30, 9, 9:30, etc. So this column shows the total number of employees working at specific shifts. Right. But our objective function was to minimize the total overstaffing and understaffing. So we're not just finding CI minus DI, because for some of them it becomes negative, right? Some of these values, CI is, for example, CI here is less than DI, but some others CI is greater than DI. So we need to find the absolute value. That's why here we have the absolute value. ABS in Excel stands for absolute. So these are going to be actually the summation of these going to be our objective function. So there are 30 values here. I'm going to actually set it here, over on. This is going to be our objective function. I'm going to set it as sum of these values. Okay. Right now is 103 people because of this random schedule that I have. Okay. We need also to have another input. Another input is that we only have 35 people. So we have to make sure that whatever a schedule we have come up with for each period, the 14 period that we have, the summation of those people that we have assigned to work at each shift, they shouldn't exceed, they should be exactly 35. It should be less than 30. So this cell should be the calculation of the summation of all of these shifts staff number. Summation. Not sure if it's correct. Should be 14. It's very easy to make a mistake. But which right now is not. Okay, so this should be actually another constraint. You have to make sure that the total number of staff that we are using in our schedule should be exactly 35. Right now it's not. So for example, if I put 2, this is going to be a feasible solution. All right. So now let's actually put this into the solver. So this is pretty straightforward. This is our objective value. I have set it up here because we could actually use some range names here. So I'm gonna give this a name. Range names. This is going to over under our objective function. This could be used, and this could be available. I'm gonna name these 2. What else we have? We have a staff plan. This is going to be a staff plan. I'm gonna name these 2. And the other. Let's go to data type solver. So this is over under, which is our objective function. We want to minimize this value, okay? Minimize the total number of overstaffing and understaffing. By changing, what should we do with decision variable? This is going to be our schedule, which is like 14 time period schedule. So this is going to be our decision variable. I'm going to add constraints right now. So the only constraint that we have is the total number of staff that we assign in this schedule should be exactly equal to 35. That's the only schedule that we have. Also, we need to have the integrality constraint. So I'm going to add the integrality constraint too. So these values must be integer. All right. So as you see here, the name change, the range names have been applied. This is over under of objective function. The decision variable is a staff plan. You want the staff plan to be integer values. And the total used staff should be equal to available budget. I'm going to call this budget. All right, good. Our constraint is set. We cannot have a negative number of employees working, so this must be checked. This is the non-negativity constraints. Again, because this is not a linear programming, because the objective function has an absolute value, right? CI, absolute value of CI minus DI. So we cannot use simplicity algorithm that we use so far. That's only for linear programming. So I'm going to use the GRG non-linear because it's a non-linear program. I'm going to go to the options here because this is going to be actually a pretty heavy actually problem to solve. Depending on your system, how much RAM does it have, the CPU power, etc., etc. It might actually take some time to solve this problem. It's not going to be instantaneously. So you might want to, depending on your system, you might want to actually put some a stopping point. For example, set this the maximum time as 30 seconds, 60 seconds, etc., etc., or the integrality optimality set it to 10% or whatever. Okay, so let me try with this 30 seconds to see if it can actually find the optimal solution. All right. So if you remember, for other problems, when I hit OK, solve here, it instantaneously was able to solve the problem. But this is a heavier problem, and it's a more difficult problem because it's nonlinear. So it's actually going to, I assume it's going to take some time to run it, especially because my RAM is using up. So as you see, it's just running. If you look here, it's just objective function, how many of sub-problems is run, the comment. So it does all these computations, still working. I have mainly I have 8 GB of RAM, but I have opened up a lot of problem here. All right, so it couldn't actually solve the problem to optimality, but the solver was stopped by maximum time, which was 30 seconds that I put. Okay. So if I set a stop, it's gonna give me the solver stop at user request. So it didn't find the optimal solution. It just stopped because of the 30 seconds time limit that I put there. Okay. So that means that it would require more time to run. Okay. So the solution that I have so far, this is the solution that I have so far. The staff plan is to have 8 people working on 6 a.m. to 6:30, to have 2 people to 6:30 to 7 a.m., 3 people 7 a.m. to 7:30, 0 people for 7:30 to 8 p.m. And we are using all 35 people that we have, and our objective value, which is the total number of overstaffing, understaffing, is 35. If I run into optimality, which is not right now, it could actually drop. I'm not sure. So let me go back here and change this maximum time. I'm gonna just get rid of this and run it again. All right, so it was optimality. So this is actually the optimal solution. This was optimal solution. So instead of 30 seconds, it actually have good 32 seconds. It would have stopped. Right, anyway, because it reached the solution. All right, so that's about it. So this is, as you saw, this is a more difficult problem. This is a different type of problem. It's not a linear programming. It's a non-linear programming, and it has a lot of actually constraints and computation. So it actually run more. It needed to run more time than our previous problems.